time for us to do some practice with using spherical and cylindrical coordinates. Now, because it's a different kind of coordinate system, it can take a little bit of time to get used to, which means practice. The more you practice, the more you start to build up your intuition, and you're able to say, really, I can understand how things get described in one coordinate system versus another. Now, in all honesty, it will be a while before we get to use this extensively, but when we do use it, it'll be a powerful tool to help us describe things and turn hard problems into slightly less hard problems. And isn't that a great thing to do? Now, if you're following along with the video, make frequent use of that pause button so that you can say, let me try this problem first and see how I do. Sometimes you might get stuck, hopefully not too often, and when you do, unpause and let's work together and figure it out. All right, well, let's begin. So for our first problem, give the point 1, 1 root 6 in cylindrical and spherical coordinates. Now, when you see something in the form parenthesis, number, comma, number, comma, number, that's how we represent things in Cartesian coordinates. So what do we have? Well, we can get a quick sketch of where that point is. So it says x equals 1, y equals 1, z equals root 6. So we move 1 over in the x direction, we move 1 over in the y direction, and then we move root 6. Now root 6 is somewhere between 2 and 3, so let's say it's here. So this is 1, 1, root 6. And so we've moved 1, 1, and root 6 up. All right, so that's our point. Our goal is to say, well, how can we describe the location of that point in different coordinate systems? So we need to go through and think about cylindrical and spherical. Now, cylindrical, we really have three things. We have r, theta, and z. Now, the good news is that z is the same as before. See, if z was root 6 here in our Cartesian, our rectangular coordinate system, z is still root 6 in our cylindrical coordinate system. So that makes that one pretty simple. Now, as far as r and theta are concerned, that's looking back in polar. So what we can do is we can say, well, hey, let's look from above. And when we look from above, what happens is we're essentially looking straight down the z-axis, and we see the xy plane, and our point would be here, where we've moved 1 over and 1 up. And we say to ourselves, okay, well, what's the angle? Well, we can see that the amount of change in both x and y are equal, so that would be at an angle of pi fourths, 45 degrees. So that says theta is pi fourths. Now, how about r? What can we say about r? Well, we have a triangle, 1, 1. The missing side would be root 2. So we can use Pythagorean theorem, right? Of course we can. So root 2, pi fourths, root 6. Good. Now, that's cylindrical. What about spherical? Well, that's going to be different. Because spherical, we've got to do slightly different things because it's different types of descriptors. So what do we have? Well, in our spherical, we have our rho, our theta, and our phi. Now, the good news is theta in spherical is the same as theta in cylindrical. And therefore, we can just copy. So, there we go, pi fourths. Now, how about rho? Well, rho is how far are we away from the center? Now, when we say the center, I should say really the origin. In other words, what's that distance? Well, so for rho, we can even say rho squared is 1 squared, the x-coordinate squared, the y-coordinate squared, plus root 6 squared. Or if you like, 1 plus 1 plus 6, which is really 8. Now take the square root, and get that rho is 2 root 2, or square root of 8, whichever one you prefer. Both are fine. 2 root 2. That leaves us with phi. Now, one way to help understand phi is to look at a good slice where we can capture what phi does. So what I'm going to do is I'm going to say, well, let's suppose I have theta equals pi fourths, because that's where we know the point lies, and I'm going to just look in that slice. When we do that, what we'll see is the following picture. We'll see our point, which is up here. We know how far up we moved. Namely, we moved up a vertical distance of root 6. We also know how far out we came. In other words, this length down here is what we'd call r. That's root 2. So we have one side is root 6, another side is root 2. And then we have our third side. Now, where does phi fit into this picture? To see that, we have to recall what phi is. So phi says if you start with the positive z-axis, how far do you come off? So in particular, phi would sit right into there. That's where phi is. But the nice thing is that this angle matches with that angle. So I can slip it into the triangle. Now, if you don't like that, the other way to do it is you can say, hey, this length up here also matches with root 2. Just do a translation. But the point here is that now we can fit phi into a triangle, and we know the lengths of two sides. That's a good number, especially when it's not just any triangle, it's the right kind of triangle. So thinking about phi, we say, what lengths do we know relative to phi? The answer is, well, we know the lengths of the opposite and adjacent sides. And therefore, we should use tangent, because tangent relates opposite and adjacent. So our conclusion is the tangent of phi is equal to the opposite, square root of 2, over the adjacent, square root of 6. Now, if you clean this up, you see 2 and 6 both have factors of 2, so you can break the square root of 6 downstairs into square root of 2 times square root of 3. Cancel, and this is really 1 over root 3. So we could say that phi is arctangent of 1 over root 3, because phi is arctangent of 1 over root 3. That's why we can say it. Now, do we happen to know what the arctangent of 1 over root 3 is? We could look it up, and if not, we can use a calculator. But this turns out to be a nice angle. And it's 30 degrees, or if you like, pi over 6. Pi over 6 is for all us calculus fans. We like doing calculus in radians. And if you think about the picture, it should sort of match with the picture. And oftentimes you say, well, oh, it's like pi thirds or pi 6. Well, which one is it? Well, if you look here, you say, well, it's not a very steep angle that we've come off. So it should be the smaller one. So that matches with our intuition. So we now can put that in as pi 6, and we're done. Now you might want to say, wait, don't we need to put a list? And here's the thing. I don't know of one universal way to list things that everyone will agree on. So for example, if I say a point in cylindrical is this, I don't think everyone will say, well, you should list it in the order r, z, theta. So what we'll do instead is we'll say, well, our point is r equals this, theta equals that, and z equals that. So this is good to go. And so we're done. We really are. Good. Oh, nice. Good. All right, well, good warm-up problem. Now let's try some more. So, our next problem. Identify and sketch the surface rho equals 4 cosine phi. So we start thinking, Now the problem is we're not so used to working with our new coordinate system. Now first off, let's ask the question, which coordinate system are we in? So what we do is we look at what kind of variables are being used. We see a rho and a phi. So rho and phi signal that we're doing spherical coordinates. Okay, so we're in spherical coordinates. So we say, all right, well, let's see if we can maybe get some insight by translating back to what we know. So in our case, what do we know? We know the Cartesian coordinates, the rectangular coordinate system. All right, so we're going to think about how to convert back. Now, when you're thinking about doing the conversion, you should basically remember there's 3 important rules. And if you remember these rules, in addition to polar, you can pretty much do everything. So the 3 important rules are rho squared equals x squared plus y squared plus z squared. That rho cosine phi is equal to z, and that rho sine phi is equal to r, where r is what you encounter when we talk about our polar coordinates. So looking at this, we say, well, we don't have any of those. But we kind of are getting close, right? Rho, that's not so far off. All these involve rho in some way. We're going to say, well, we like rho squared. Maybe we should square it. But if we square it, we have to square cosine squared. And then, that's getting us into trouble. Okay, hold on. Let's look at this other side. There's a cosine phi. We say, wait, there is this expression, rho cosine phi equals z. An idea. What if we could make cosine phi look like rho cosine phi? Well, how can we do it? Well, it's missing a rho. So we say, okay, let's add a rho. So how do you add a rho? You multiply. Now, as long as whatever we do to one side, we do to the other, we're okay. Now, there is a small technicality about what about rho equals 0, and my advice to you is don't worry about the small technicality. It's so small and unimportant that it never will come into play. So multiplying both sides by rho will lead us to rho squared equals 4 rho cosine phi. And now we're looking at this kind of equation and we're going, nice. Well, why would we say that this is nice? Well, because we say, hey, rho squared, that has a nice formula attached to it to convert. And rho cosine phi, similar thing. So this will become x squared plus y squared plus z squared is equal to 4, and rho cosine phi becomes z. Aha! Now we're feeling good. In fact, we can even start to identify what we have. Do you see what it is? There's an x squared, y squared, and z squared all there. That means sphere. This is a sphere of some sort. Well, let's get more precise. So let's start to dig into it a little bit more. I can move the 4z across. So x squared plus y squared plus z squared minus 4z equals 0. Now, do our familiar complete this square, because we really want this z squared minus 4z. We'd like this to be, z plus or minus something squared. Now you say, well, what do we need to put in so that this square is completed? We want to complete the square. Well, that's a good and worthy goal. So we say to ourselves, all right, take the middle term, negative 4, divide by 2, and then square that. So negative 2 squared would be 4. So if you added 4, then this becomes z minus 2 squared. Well, if you add 4 there, you have to compensate somehow so that the net result is that at the end, it's the same as what you started with. And the way we do it is we also add 4 to that side. Good, good. Now everything's the same and we're happy. And we can start to identify what we're dealing with. So not only is it a sphere, we now know some more about it. We know the center is at 0, 0, positive 2, and we know the radius is also 2. And so we have that this is a sphere. And now we've identified definitely, we know everything about the surface. Last thing is sketch. Okay, well, this will be a little bit sketchy, but not so bad, right? We can draw spheres. So we throw in some coordinate systems here. There we go. Got my axes, and it says our center is on the z-axis, where we've gone up 2. And then our radius is 2, so it's actually going to sit right on the xy plane, and then just go 2 in each direction. Now, the way I tend to draw spheres is I draw a circle, and then we add sort of an equator. And there we go. There's our sphere. We'll put a little 2 there. All right, good. Well, that shows you, spherical coordinates. It's not too surprising that we get a sphere, but of course, it's not just any sphere. It's a sphere sitting right on the xy plane. We'll see probably that some spheres are easy to work with in spherical coordinates, definitely spheres centered at the origin. Some spheres are okay, and some spheres are crazy. We'll get into that as we do more and more problems. And the more we do, the more that we know. Well, good. So let's do some more. All right. Next problem. Rewrite rho equals 1 over cosine phi plus sine phi in cylindrical coordinates as a function of z and sketch the surface. All right, well, that's interesting. Now, what is it currently in? We see there's a rho and there's a phi. Well, rho and phi tells us that currently we're in spherical coordinates. So we're in spherical coordinates. We want to switch to cylindrical. All right, well, so we just have to think about our rules. Now, our rules, not so bad. We know a couple of basic ones. We always, so you can say, look, rho squared, that's just a good one to remember. X squared plus y squared plus z squared. Now, that's not really cylindrical, but it's not so hard to make it into cylindrical because x squared plus y squared equals r squared. But for right now, we'll just leave it as is. Rho cosine phi is z, and rho sine phi is r. So when we're thinking about converting, we're asking ourselves, okay, how can we get things like rho squared, rho cosine phi, rho sine phi? Those are our nice things to convert. So we're looking for those things because, well, we like things to be nice. We love ourselves. We want us to have the best time when we're doing these problems. Now, one thing that I see is there's currently a fraction. Fractions. What a headache. We want to get rid of them. How do you get rid of a fraction? Well, one way is you can do what's called cross multiply. So if you multiply this across, what do you get? Well, you can get rho times cosine phi plus sine phi equals 1. So that's getting rid of fractions. Now, distribute. So I can take the rho and I can multiply it through. If we do that, rho cosine phi and rho sine phi equals 1. All right, good. And now we say, hey, perfect. Rho cosine phi becomes z. Rho sine phi becomes r. So, z plus r equals 1. Or, oftentimes we'll write it as z equals 1 minus r. All right, so that is cylindrical coordinates. Good. Done with that part. There's another part, though. The other part says, sketch the surface. That we have to think about. So let's sort of talk about two approaches. So the first approach says, do we recognize it as kind of close to something we know, and can we modify? So there is a surface that hopefully we know, and it's called z equals r. So that's the surface that we'd like to be able to recognize. Now, what is it? Well, it's a cone. It's a cone that goes up in this way. So that's what z equals r does. So there we go. Z equals r. Now, we start with what we know. Now we start to gently massage and treat our problem very lovingly, kindly. Because if you're nice to the problem will be nice to you. All right, so we ask ourselves, what can I start doing to this r to make it look like 1 minus r? Well, let's start with a minus. Suppose now we take our basic shape and say, instead of saying z equals r, let's say z equals minus r. What's the effect? Can you see it? The effect is we're going to turn it upside down. So if it was going up, now it's going to go down. So that's what the minus r does. All right, that's not so bad. We can believe that. Well, especially because it's true. That helps us to believe it when things are true. Now, that's the minus r. Let's think of the 1. What is that doing? Well, the 1 is doing what? Well, it's like we're taking z, and which is negative r, and adding 1 to it. Well, that says everything that you see with z right now increased by 1. So the effect is, if we're here, we're going to up, just doop, doop. So it's a vertical shift up. So z equals minus r plus 1 looks like an upside down cone where you start here at 1 and then you open down. All right, now I said we'd do this in 2 ways. So that's one way. What's the other way? Well, what I would say is to do the following. Let's look at what I would call the RZ half plane. And this is saying, look, z equals 1 minus r, where do you see theta? The answer is, there is no theta. Okay, so when you don't see any theta, what that means is you get this beautiful rotational symmetry. So what you can do is you can say, well, let me figure out what I'm spinning. And if I know what I'm spinning, I'll know what my shape is. So I'm just going to look in terms of r and z. So right now I'm not three-dimensional. I'm just saying, let's look in sort of a half plane, and then we know what to spin, and that will give us our whole shape. So what do we have? Well, if I were to say z equals 1 minus r, if you're not comfortable, think of it as y equals 1 minus x. It's just different names for variables. Y equals 1 minus x is like, that's a line. It has a intercept at 1, slope of minus 1. And so it's still a line. Intercept at 1 and a slope of minus 1. So what it looks like is we start here and we go down. Now, that's z equals 1 minus r in the half plane. To get the full picture, we now say, look, there's no theta, spin it around. When you spin a line, what you're going to end up doing is you're going to spin it and it's going to become a cone. Sorry, I can see that my modern interpretive dance skills are not quite what they used to be. You have to imagine that you can visualize spinning. All right, so now we spin, and lo and behold, what we'll get is what we should get, right? An upside down cone. That starts here at 1, and there we go. So whichever way helps you to understand it, use that method. It's nice to be able to adapt to both, because in certain settings, one is more useful than the other. And it's just a matter of practice. And of course, practice is always important. All right, well, let's do some more practice, and let's go on and do another problem, right? Of course. So for our next problem, here we go. Sketch the region and find the volume of all points. Oh, all of them. All right. Satisfying z minus 1 less than or equal to r less than or equal to 1/3 z plus 1. Okay, well this should be interesting. What do we do? Well, let's think about what we have here. Now, we have a sequence of inequalities here. See, there's another equality there. 1, 2, boom, boom. So we're going to break it into two parts because that'll help us really understand a little bit better about what's happening. So let's call this 1. We'll call this 2. So for 1, we're really saying z minus 1 is less than or equal to r, or if you like, we could say that says z is less than or equal to r plus 1. All right, so that's number 1. Number 2 says what? R is less than or equal to 1/3 z plus 1. Or, let's try to get z by itself. We could say 1/3 z is greater than or equal to r minus 1. Now, if you're curious, like, wait, why did he flip the sign? Well, because I'm just flipping what I'm calling left and right. So I've moved them across. Or we could say z is greater than or equal to 3r minus 3. Okay, so what are these shapes? Well, again, we can go through and think about it in a couple of different ways. What I'm going to do is I'm going to try to get an understanding of sort of what's happening if I look in a slice. Because I see that there's no theta involved in this problem, which means that I have that nice full symmetry around the z-axis. Whenever we see no theta involved, it means it's the same for every choice of theta. Perfectly symmetrical around z. So let's start by sort of getting an idea here. I'm going to mark here, this is r and z. And let's see. Z is less than or equal to r plus 1. So I come over here to 1, and I start the line up. So this is z equals r plus 1. And on the other hand, I have z is greater than or equal to 3r minus 3. So that says I'm going to come down to -3. And then what's going to happen is I'm going to go up, and probably go up mildly fast. I don't know, but something like that. All right, good. There we have it. All right, so what's the case? Well, I have to be below this top line, because I have to have z is less than or equal to r plus 1. So I'm below there, but I have to be above this bottom line, which means that I'm interested in the points which are in between. And there we go. Now let's take a second here and figure out a couple of things. In particular, I'm very interested in understanding this intersection. All right, well, how do we know when two things intersect? They have to be equal. So that would tell us we need r minus 1 equal to 3r minus 3. So we can move things around. And so we subtract r, we add 3, and what do we get? Well, what we get is we get 2r equals 2, or r equals 1. Okay, well, our picture's not very accurate. That sometimes happens with pictures. You gotta be careful, right? You gotta be careful. Okay. Good. Oh, whoops. I had a copy error. I was looking in the wrong place. I saw r minus 1. It should be r plus 1. Okay. Then it means that this should be 2r equals 4, which means r equals 2. Okay, still not great, but not terrible. So r equals 2. What is z? Well, 2 plus 1 means this would happen at z equals 3. Okay, now, this is just one cross-section. Spin it. And what do we have? What you end up with is you have the following three-dimensional object. You have cones. See, whenever you spin a line inside this RZ, you're going to spin and you're going to form a cone. So we have a cone sort of drilled out of another cone. So that's our basic shape. A big cone with a small cone missing at the peak. Okay, so there we go. There we go. So now we have kind of a rough idea of the shape. This is a sketch, all right. We're not done. We have the sketch, but we also have to do a second part, which is we need to find the volume. So how do we do that? Well, let's just do a quick refresher. So a volume for a cone is 1/3 base height. And the base of a cone is a circle. So usually we write this as 1/3 pi r squared h. Now, the base doesn't have to be a circle. It can be any shape you want. But, all right, so there's our basic setup. Now we say, okay, so our shape, it's a big cone, subtract a little cone. So our volume is going to be our big cone, subtract our little cone. So we say to ourselves, okay, let's think about the big cone. What's true? Well, first off, what's the radius? The radius is going to be, in both cases for big or small, it's always going to be 2. So it's this distance across. So it's going to be 1/3 pi 2 squared. The height of the big cone is going to be from +3 down to -3, which is 6. Then the little cone, 1/3 pi, still the same radius, 2 squared, but now the height is from 3 down to 1. Okay, so that means 2. So, well, we're almost there, and, well, now do a little bit of multiplying. So we get 24/3 pi from the first one, because 2 squared is 4 times 6 is 24. 24/3 pi. Subtract. Here we'll get 2 squared times 2, that's 8. So that's 8/3 pi, which leaves us with 24 minus 8 is 16/3 pi. And that's the volume. And there we go. There's the shape. There's the volume. And we're done. Woohoo! We did it! Success! Success! All right. Well, good. Let's do one more. One more problem. Okay. So last problem. Rewrite rho squared, which is negative secant 2 phi, in Cartesian coordinates and in cylindrical coordinates. So, all right, cool. Interesting. Not quite so clear what's happening. Not yet, but let's think about this. What can we do? Well, first off, we do see a phi, which is great. There's a catch. It's not just phi, it's 2 phi. We don't want 2 phi. See, because our formulas for conversion involve only a single phi. So, in other words, we would be happy if we saw something like a rho sine phi, because we know how to handle rho sine phi. That becomes r. Or we'd also be happy if we saw rho cosine phi, because that would be z. But we aren't happy with 2 phi. So we got to get rid of the 2. So we say, okay, well, let's use some identity. And then we look at this and say, secant double angle identity? I don't think we were asked to memorize that, because we're not going to ask you to memorize that. It's not really an identity that gets used. So we have to start thinking, well, okay, so how are we expected to do this? Well, let's start thinking about things that we can do. It's like, well, all right, I don't know the double angle identity for secant. Can I rewrite secant? Now, whenever you have a problem with trig and you ask the question, can I rewrite it? The answer 100% of the time is yes, you can. It really boils down to, and how? Well, for us, the way we rewrite it is we say, here's what we'll do. We can replace secant by 1 over cosine. Now that's good. Why is that great? Well, because we may not know how to handle secant double angle, but cosine double angle is great. So there we go. And not a big fan of fractions. Let's get rid of the fractions. Multiply across. So rho squared cosine 2 phi is -1. All right, progress. All right, well, now let's do the double angle identity for cosine. Now, what is the double angle identity? Well, it turns out that cosine 2 phi is cosine squared minus sine squared. Okay. That looks good. And you can multiply the rho squared in. So you can, if you distribute here and then do a little bit of rewriting, this becomes rho cosine phi squared minus rho sine phi squared equals -1. Now, right now, we're kind of a little bit negative. In fact, we're very, very negative. And so what we can do is we can actually clean it up just a touch. And the way we clean it up is to do the following. We'll multiply through by negative. So it's probably going to be better to say rho sine phi quantity squared minus rho cosine phi quantity squared is equal to 1. All right. Now we can begin. So, what comes next? Well, the next thing for us is to replace rho sine phi by r, rho cosine phi by z. All right, let's do that. So, if we try that, what do we get? Rho sine phi becomes r. So we get r squared. Rho cosine phi is z squared, and that equals 1. Okay, now how about r squared? What can we do with that? Well, that's x squared plus y squared minus z squared equals 1. And notice the first one, that's our cylindrical, and our second one, that's our Cartesian. And now, we're done. We're actually done. Woohoo! Because that's what it asked us to do. It said, hey, rewrite this in a different coordinate system. And there you go. There you go. Great. Well, fun problem. Fun problem. Of course, they're all fun once you're able to solve them. And the way you get to solve problems is you work on them. And you do them. And the more you do, the better you get. So keep working on it and keep getting better. All right. Have a great day. Hi, guys. It occurred to me you might be interested to ask the question, what does this look like? It's not really part of the problem, but for those of you who are wondering what it looks like, this is something we're going to get into in a later session. I'm just going to do a quick sketch of it right now. It's called a hyperboloid of one sheet. And what it looks like is it's kind of what you might see if you were thinking of an hourglass shape. So that you have coming down and then going back out. Now you might sort of start to ask yourself the question, is this reasonable? Now that's a great question to ask. And so let's see if we can't convince ourselves that this is reasonable. So if you think about minus secant of 2 phi, well, I'm going to look at some very special ranges for phi. Notice if you plug in phi equals 0, you get a negative value, but that's rho squared. You can't have rho squared be negative. So that says if I'm going straight up the z-axis, I don't see anything at all, which is good because our hyperboloid of one sheet, our hourglass, doesn't hit the z-axis. In fact, minus secant of 2 phi is going to be negative when we have 0 less than or equal to phi and all the way up to pi fourths. So in particular, if we have this sort of angle of pi fourths, there's nothing up here inside of that range. And it's also negative when we have the following, namely 3 pi fourths less than or equal to phi less than or equal to pi. So in other words, it's also going to be missing down here. So that if you look down in that cone, no part of the surface is in that part of the cone. So we missed what's up here in that top cone, we missed what's down there in the bottom cone. And then what's really happening is we kind of are trying to approach the cone as we come in from the two sides. Now, at the halfway point, which is the xy plane, you have to remember, be careful, that is phi equals pi halves, not phi equals 0. So at the xy plane, you'd have 2 times pi halves, which is pi. Secant of pi is minus 1. And therefore, what you end up with is a minus. A minus 1 makes a plus 1. So that in the xy plane, we go out rho squared equals 1, or rho equals 1. So we have that circle of radius 1. So this is, in fact, a reasonable shape. We'll get more into this type of shape later on. But I just wanted to throw that in case you're wondering, wait, what does it look like? I want to know. Well, good for you. You should want to know. It's good to know stuff. All right. Thanks for sticking around.